Hey everyone. In this video, I'm going to talk about one of the examples in our textbook in chapter 3, which focuses on the distribution of heights and weights of people and how this relates to the central limit theorem and normal distributions. And particularly, one thing to keep in mind is that although when we talk about sampling distributions, we often kind of invoke the normal distribution by virtue of the central limit theorem. There's no reason to really expect that any random variable itself that represents direct measurements in the world has to be normally distributed, right? But there are some examples, and height and weight is height in particular can be one of those examples, because we can think of height or a person's height being affected by a lot of small additive factors, right? And by virtue of height being ultimately influenced by a lot of small additive factors, kind of genetically, we can basically posit that the central limit theorem here also applies, and that kind of implies that the distribution of heights in the population should also follow a normal distribution, right? And so in the book, there are some kind of basic graphs of probability or of a distribution of heights of people. And we're going to look at a specific example rather than just drawing some distribution functions. And what I did is I found some data that we can look at, which is actually from an anthropology data set, which the anthropologist Nancy Howell conducted basically a census of a foraging population in the 1960s in Africa, and collected data on people's height, weight, age, and gender. Okay, and we're going to use this data set from this anthropology study to kind of look at the same distributions that we have displayed in the Gelman book, right? So the first thing we're going to do is we're going to load our the packages that we're going to use as well as the raw data. Of course, as always, we're going to load the tidyverse, and I'm going to show you an example of combining separate independent plots in one plot in ggplot. And in order to do that, there are different packages that allow you to do that, but the one we are going to look at, that we're going to use, is the cowplot package. Again, this allows us to combine multiple ggplots in one figure ultimately. Okay, so we're gonna load this data set. It's also on our Studio Cloud. It's howl1.csv. There are two different things. In order to kind of replicate the same graph that we have in the book, we want to exclude children. We only want grown adults and compare heights of grown adults. So we filter out anyone with age smaller than 18. And then just for plotting, there's a variable male in that data set, which is just a dichotomous indicator, which takes a value of 0 or 1. And for plotting later, I'm going to recode this to a gender variable with male and female as character outcomes, because ultimately that will make our plotting, or the legend for plots, a little bit easier. Okay, so after we did that, let me just show you the data frame. We have a table. We have 352 observations. They were surveyed or part of this census. We have 5 separate variables, as I mentioned: height, weight, age, and male and gender. That's the recoded variable ultimately. Okay, and in case you're confused, height and weight here is based on the metric system. So height is in centimeters and weight is in kilograms. Okay. Then the first thing we want to do is we want to plot the histogram and the densities of this distribution of heights, right? And remember, we're just, for the first figure, we're just looking at the basic distribution across all individuals, right? And so in order to do that, we first create a ggplot with where the only aesthetic mapping is height, and we want to create a histogram. In general, the default behavior of the histogram, the geometry, is that this on the y-axis would just show the count, but I want to overlay not only the count but also the density, so the kernel density of that distribution. So I specify here by specifying y equals ... density. That's using basically the computed density for that distribution, and so that basically just all this does is it's still showing the same histogram, but instead of showing the histogram with the count on the y-axis, it's now showing the density on the y-axis, and that helps us to put the density, the kernel density itself, on the same plot as an additional layer. Okay, so that's the first plot, and then we're creating a second plot, which is again based on the height, but the only thing here is that in addition to the histogram, we will now separate the density, and we're adding an additional aesthetic mapping for this density geometry for color and fill, both dependent on gender. So that means in one case we're looking at the histogram and the density for the entire population, and in the other plot we're looking at the density, the kernel density, for men and women separately, right? And I'm moving the legend of this for this plot to the bottom. Okay, and now this is why we use the cow plot. Now we create a plot underscore grid, which basically just combines those two plots, P1 and P2 that we saved previously, in one common in one display, basically. Okay, and this is the result of this plot. And we see, despite the fact that this is not the data that is used in the Gelman book, we see a very similar pattern that we kind of wanted to examine. When we just look at the height itself, the distribution of height itself, we see that it doesn't really follow a normal distribution. There are kind of two peaks here. And the argument here is that we have to keep in mind that men and women tend to have different heights. Men, on average, are taller than women, of course. So, despite the fact that the central limit theorem for height kind of holds for heights as a measure that is determined or influenced by a lot of smaller factors, the distribution of heights doesn't follow a simple normal distribution, because in fact it is a mixture of two normal distributions, right? So now we in the bottom panel we look at the kernel densities for men and women separately, and we see that those are two distributions with obviously different means, different expectations, and we see that ultimately both men and women by themselves, the distribution of heights follows a normal distribution, or I mean not perfectly, but you know, at least the shape is more similar to a normal distribution, and combining both together ultimately results in a distribution that is bimodal, and obviously does not follow a normal distribution. Okay, so that's kind of recreating the same example that is discussed in the book, but now with like some cool anthropology data, and finding the same result. Okay, we can make this plot a little bit nicer looking and kind of make this a little bit more clear how closely these distributions follow a normal distribution. We can do this by adding an additional by adding an additional layer, an additional geometric layer, where we basically just add a kind of theoretical probability of a theoretical density of a normal distribution with the specific mean and standard deviation that we observe in our actual height data. Okay, so basically this section up here that we just added adds this theoretical normal distribution with our given mean and our given standard deviation for height. And we do the same thing here, adding theoretical normal distributions for height for men and for women by using the specific averages and standard deviations, and just by using the geom function command and denorm, we're just plotting. This is not based on data. This is just plotting a theoretical density of a normal distribution with a given mean and a given standard deviation. And we can use that to kind of compare our empirical densities, our empirical kernel densities, our distributions versus kind of theoretical normal distributions. And this kind of confirms again here that the distribution of heights, just aggregating men and women, does not follow a normal distribution. But if we look at men and women separately, at least for women, there's a shape. The shape of the distribution closely follows a normal distribution. The distribution for men appears to have slightly heavier tails and seems to be a little bit more narrow. But overall, certainly closer to a normal distribution than the original distribution of men and women combined. Okay, so that kind of follows the same example that is covered in the book. Okay, in general, another thing that is shown in the book is this visualization of the area under the normal distribution and how much probability mass falls within 1 standard deviations and 2 standard deviations from minus and plus the mean of the normal distribution. And here I just want to show you some code to recreate this visualization and also to kind of practice thinking about normal distributions. So here we start a ggplot without any data, because we're only using the geom function command. We're not plotting any empirical densities. We're just plotting a theoretical normal distribution, a standard normal distribution, in fact. In order to do that, we first have to specify the limits of our x-axis. We're plotting the standard normal distribution from -3 to 3. We're changing the theme here a little bit just to make it look closer to the actual graphic in the book. And then again, we're adding this geom underscore function command. The function here is denorm, which again is just the probability density function of the normal distribution, the standard normal distribution. And we're making this line a little bit thicker. Okay, so and we're adding some additional theme specifications where I'm just removing the y-axis and some axis labels just to make the plot a little bit cleaner. Okay, so what's the result of this? Just adding this just results in the basic standard normal distribution centered at 0, and of course in a standard deviation of 1. Okay, so what does this mean in terms of the probability mass in that described by the area under that normal distribution? We can basically kind of separate 2 different areas. On the one hand, we have the area between -3 and 3, where we just now shade as black. We have a gray area between -2 and 2, that is between here and here, that is now dark gray, and then we have light gray between -1 and 1 to just basically shade this area under the curve, right? And so this is again using the stat underscore function command with again our denorm function, and this allows us to directly kind of just color and shade areas under a specific under a specific curve here under the normal distribution. Okay, so this is already one step further in kind of recreating that plot that you saw in the chapter. And now we want to, in addition, compute the area under this curve from -1 to +1 standard deviations from the mean, so this light gray area. And in addition, we want to compute this darker gray area on the left side and on the right side to kind of confirm what we already said in the previous videos and in the book about how much probability mass is within 1 and 2 standard deviations from the mean of the standard normal distribution. Okay, and we can add those numbers by using our now known geom text geometry. So we just add a text label. We manually set this position. And we, as a label, we define on the one hand for our center area, we just compute the difference p norm 1 minus p norm minus 1, which is kind of, if you are confused about that, go back to the previous video where I talked about the normal distribution and how to compute these cumulative probabilities of the standard normal distribution up to 0.1, up to x equals 1, and the probability of x being up to -1. And if we subtract those two probabilities, we have the probability between -1 and 1 of that standard normal distribution. I'm just multiplying this by 100 and adding percent here using paste to make this be formatted as 68%. So 68% is the area, the probability mass between -1 and +1 standard deviations from the mean of a standard normal distribution. Okay. In addition, what I'm doing here is I'm adding the area for this dark gray area as the difference between the area up to x equal 2 and the area up to x being equal to 1. That would of course be the both this area as well as this area, since the normal distribution is symmetric. And we know that 68% plus 28% approximately will combined sum up to about 95%. And so we know that between -2 and 2 standard deviations from the mean, that's basically 95% of the probability mass of the standard normal distribution. Okay, so that kind of goes both through the math and also shows you some additional techniques for visualization in ggplot to plot kind of theoretical normal distributions and kind of add additional visualization features. So I hope this was helpful and you can use some of these techniques in your own visualizations. Okay. Lastly, the last thing that is mentioned in the chapter is this distinction between normal distributions and the log normal distribution. The log normal distribution is basically a distribution that is in raw terms not normally distributed, but if we log the distribution, then the log itself is normally distributed. And one example for that is in the book, at least, the weight, people's weight, because it has a heavier tail, so to speak. And so we're just going to try to replicate this using this anthropology data set. And so in the first case, we have here just now again the empirical density for weight, and we add a theoretical normal distribution for with the same mean and same standard deviation, and we see that indeed the weight variable is not symmetric. It's slightly skewed, has a slightly heavier tail on the upper end, and therefore does not really follow a normal distribution. Then if we take the log of weight and plot the same distribution, we see that this follows more closely, not perfectly obviously, but more closely a normal distribution, right? So one thing to keep in mind here is that overall it is often helpful to model random variables that are all positive, that only take positive values on the logarithmic scale, because that ultimately then on the logarithmic scale, that variable is not bound anymore, and that can be useful for modeling. So one example is weight, but you could also think about political science examples, things like GDP, or other purely positive values can often be modeled more appropriately using a logarithm. Okay, just to mention it, if we have kind of a log normal distribution, or if we take the log of a distribution, if we can take the average of that log and the standard deviation of that log, and if we take the exponent of those, what we get then is the geometric mean and the geometric standard deviation of that measure. Okay, so if you ever encounter the concept of a geometric mean or geometric standard deviation, it's the mean and standard deviation of the log measure, essentially. Okay, or the expectation of that. Also keep in mind, of course, the original scale here is skewed. The logarithmic transformation is nonlinear, and it pulls the extreme values on the upper end closer to the distribution, and therefore leads to a more symmetric distribution on the for the logarithm of weights. So it kind of helps us deal with these kind of extreme values. But in general, one thing that is important to emphasize is that the reason we perform logarithmic transformations is not necessarily to get the distribution closer to a normal distribution, but rather to transform the kind of transfer multiplicative models into additive models. Okay, and this is a point that is mentioned in the book, and that we'll discuss in more detail later on in the semester, right? So as soon as we're invoking logarithms or exponents, our models turn from a simple additive linear model. They can then be interpreted as a kind of multiplicative model, and for certain types of outcomes and certain types of variables, that can be useful to model change as a multiplicative change. Okay, so much about normal distributions and log normal distributions and how to interpret them. We'll talk more about that throughout the rest of the semester, but for now this should be enough, and in the next video I'm going to move on to talk a little bit more about statistical inference.